Hello, my name is Subah, and today I'll be discussing the research technique EMSA. Electrophoretic mobility shift assay, or EMSA, is a gel electrophoresis-based research technique mainly used to observe interactions between proteins and nucleic acids. Essentially, EMSA works on the assumption that a free nucleic acid has greater mobility or moves faster than a nucleic acid-protein complex. This procedure begins by loading a prepared sample onto the gel, which contains a radioactively labeled fragment of DNA, the protein of interest, and the protein binding site. The nucleic acid-protein complex moves slower than the free nucleic acids as it has a larger mass due to the protein binding. This separates their band locations, and the gel is able to visualize this. Ultimately, this can help us determine whether the protein of interest actually binds to a particular nucleic acid and forms a complex. When performing EMSA, there are a few items of consideration that must be accounted for. The first one is the salt concentrations, as this can affect the binding between nucleic acids and proteins. The next consideration is the selection of the target nucleic acid, since shorter fragments are cheaper, more accessible, and decrease the occurrence of nonspecific binding. The last factor to be considered is when multiple proteins bind to the same nucleotide sequence, as it makes it difficult to examine the reaction of the target protein. EMSA is a technique that has several advantages. These include the fact that it is simple to perform, highly sensitive, and is able to work in several different conditions. Although EMSA can be convenient, it does have its limitations. One of these includes the possibility of the nucleic acid-protein complex dissociating, since the samples are not at equilibrium during this process. Another limitation is that EMSA cannot detect the specific nucleotide sequences that the protein of interest occupies. Lastly, there is a possibility that the electrophoretic mobility of the complex can depend on other factors and not only the size of the protein, which EMSA does not account for. The use of EMSA can be seen in various applications, specifically in DNA repair, cell signaling, and transcription factors. For example, EMSA has been used to examine how platinum drugs and the DNA-binding protein PERP1 interact in the nucleus, presenting the role that platinum drugs play in DNA damage repair. Overall, EMSA is a common research technique that has demonstrated its value in the fields of biochemistry and molecular biology, and continues to develop into a more efficient technique for those conducting research on nucleic acids and proteins.
Created using Powtoon.